Welcome to the Horizon Audiofiles, a podcast of the Defense Horizon Journal. The Defense Horizon Journal is a professional and academic journal that features essays, reports, and analyses covering geopolitics and law, security and defense policy, peace and conflict studies, applied military science, as well as developments in weapons technology. For more information, go to www.tdhj.org.
Episode number 91. Mosaic Warfare in Ukraine. By Bjorn Hoog. Introduction. The Russian full-scale invasion of Ukraine in February 2022 has produced the most extensive large-scale interstate war in Europe since the Second World War and has provided an unprecedented empirical environment for observing the evolution of contemporary warfare. Among the most striking developments has been the rapid battlefield diffusion of distributed uncrewed systems, digital integration platforms, and decentralized decision-making practices. While these developments are often analyzed separately as elements of drone warfare, networked operations, or battlefield innovation, this article argues that they can be more coherently understood through the conceptual lens of Mosaic warfare. Although Ukraine does not explicitly use the term, many of its battlefield practices reflect core Mosaic principles: distributed low-cost systems, adaptive kill webs, decentralized execution, and rapid sensor-to-shooter integration. The Ukrainian case, therefore, challenges the widespread assumption that Mosaic warfare is primarily a distant future concept tied to emerging disruptive technologies. Mosaic warfare, conceptual foundations. DARPA's Strategic Technology Office, STO, strategy developed the concept of Mosaic warfare in response to the declining operational value of platform-centric force designs that concentrate multiple missions into a small number of exquisite, high-value assets, and to the USA's declining technological edge over its adversaries. These systems are characterized by long development cycles, limited adaptability, and rigid command and control structures, making them ill-suited to rapidly evolving operational conditions shaped by anti-access, area denial, A2AD, strategies, electronic warfare, and the proliferation of precision strike capabilities. Adversarial tactics such as system destruction warfare, which target key nodes and networks to disrupt military operations, highlight the vulnerabilities of centralized systems and linear kill chains. TAL systems. Mosaic warfare architectures prioritize loose coupling, modularity, and rapid composability, enabling force packages to be reconfigured and reassigned as missions and threat conditions change. Instead of concentrating multiple functions in a small number of tightly integrated multi-role platforms, Mosaic designs disaggregate capability into many smaller, specialized, interoperable nodes that can be combined into tailored groupings or force packages for specific tasks. In practice, this often implies shifting from large and all-inclusive, so-called monolithic platforms to smaller, more distributed, tile platforms, including unmanned systems, where expensive multitasking systems are decomposed into numerous lower-cost elements that can be deployed more widely. This design logic supports affordable mass and improves resilience through redundancy. If a node performing a given function is lost, another platform with the same function can be dispatched to restore the formation without collapsing overall mission effectiveness. The same disaggregation, however, pushes complexity upward into integration and orchestration. Tile-based forces must synchronize a larger number of heterogeneous nodes, which increases demands on communications, data fusion, and command and control. Kill webs. Traditional kill chains are typically linear and sequential. A sensor detects, information flows through command, authority approves, and a shooter engages, creating brittle dependencies where disruption at a single node can paralyze the chain. Mosaic warfare, by contrast, favors kill webs, networked architectures that provide multiple, parallel pathways from sensing to decision to effects, enabling forces to recombine available nodes, route around losses, and maintain tempo despite degradation. Conceptually, this is enabled by functional decomposition, rather than treating the OODA process as a fixed linear chain. Observe, orient, decide, act functions can be separated into interoperable elements and then recomposed into multiple concurrent paths for a given mission. This will be illustrated later through a specific practical example of a kill web implemented by Ukraine. Drawing on Zweibelson, a traditional kill chain can be analogized to a tree, a hierarchical, linear structure with identifiable trunk and branch dependencies that create vulnerable critical nodes. In contrast, a kill web resembles a rhizome, decentralized mesh of many-to-many connections that can route effects to increase speed by taking the shortest path, avoiding hierarchy, or to reroute them to bypass disrupted or destroyed nodes. Also, the rhizome structure can restructure or repair itself. Importantly, a kill web does not depend on omnipresent connectivity. Instead, networking is treated as mission adaptive, balancing bandwidth, coverage, and delay to sustain information flow in denied or high-intensity environments. A mature kill web approach is not simply more connected, it is expected to be elastic, agile, and intelligent, able to keep operating under interference or failure, rapidly assemble mission-suitable groupings, and use AI-enabled support for tasks such as group planning, recovery, and adaptive learning. These advantages come with a trade-off. Kill webs increase coordination requirements and place greater stress on C2, communications, and integration to prevent distributed flexibility from turning into distributed incoherence. Decision-making and autonomy and time compression. Effective Mosaic warfare depends on centralized intent but decentralized execution. Mission command gives subordinates purpose and boundaries while leaving them freedom of action. Decision-centric warfare adds the aim of making and enacting faster, better decisions than the adversary under contested conditions. Together, they allow lower echelons to seize fleeting opportunities without waiting for higher approval. In general, Mosaic concepts seek to compress time by accelerating the OODA cycle and reducing kill process latency. In decision-centric terms, Mosaic forces seek advantage not only by speeding up their own OODA loop, but also by complicating the adversary's ability to observe and interpret force structure and intent, thereby prolonging the opponent's decision cycle even under conditions of high battlefield transparency. By employing decoys, false emissions, and misleading movement patterns, Mosaic forces create confusion about their real force structure and intent, and then suddenly disrupt the opponent's decision cycle by revealing the actual attack path only at the moment of action. Autonomy is central in two complementary forms: human autonomy, delegated decision-making rights at the tactical edge, and machine-enabled autonomy, automation that accelerate execution and reduce cognitive load. Automation can also support distributed C2 by enabling collaborative processing and transmission of information under bandwidth limits or network disruption, and by assisting commanders in achieving detect, understand, act first effects through data-driven situational understanding. By pushing decision authority and execution capability forward, forces can sustain local initiative and effects generation even when higher headquarters links are disrupted. This resilience is particularly valuable in contested electromagnetic spectrum (EMS) environments where adversary electronic warfare (EW) threatens centralized C2 networks or detection due to radio frequency emissions and other signatures. Not every form of battlefield adaptation or technological innovation automatically constitutes Mosaic warfare. The concept refers specifically to distributed architectures in which modular tiles can be dynamically recomposed into mission-specific force packages that integrate sensing, decision-making, and effects across heterogeneous systems. While Ukraine's wartime adaptation includes many elements consistent with such an approach, including distributed UAV employment, digital battlefield integration, and decentralized execution, other aspects of the conflict remain shaped by more conventional dynamics such as artillery-centric attrition and positional warfare. Distinguishing between general adaptation and genuinely Mosaic-style architectures is therefore important to avoid overextending the concept and to clarify what specific features of Ukrainian battlefield practice align with Mosaic warfare principles. Ukrainian Battlefield Innovations 2022 to 2025. Distributed mass low-cost UXS employment. Russia's full-scale invasion began in February 2022 with the commitment of a forward-positioned and combat-ready, yet ultimately limited force relative to its political objectives, designed to generate shock and awe through a rapid mechanized drive on Ukraine's center of gravity, Kiev. The operational concept combined air assaults, most notably the attempt to seize hostile Antonov Airport, with deep armored thrusts aimed at capturing key nodes, disrupting Ukrainian command and control, and exerting pressure on the political center of gravity. Russia's force quality was arguably at its highest in this opening stage. However, troop availability was limited for the scale of the mission, and planning assumptions clearly anticipated a rapid collapse rather than sustained resistance. In practice, Russian units struggled with coordination, command and control, and logistics, and fast battalion tactical group maneuvers ran into determined Ukrainian defense. This phase was characterized by rapid mechanized movement with formations ordered to advance by road in administrative columns, which made them vulnerable to ambushes and to widespread Ukrainian use of portable anti-tank guided weapons, notably Javelin and NLAW. Importantly, rapid advancement did not end with Russia's stalled drive on Kiev. In September 2022, Ukraine demonstrated rapid maneuver at scale in the Kharkiv offensive, exploiting thinly held Russian sectors to achieve a swift breakthrough and reclaim large areas in days. From late 2022 into 2023, the war shifted more decisively toward artillery-centric attrition and positional warfare, with increasingly stable front lines shaped by fortifications, minefields, and an intense contest in reconnaissance strike. Uncrewed aerial vehicle, UAV, enabled observation, improved targeting and compressed kill chains, making artillery and ammunition supply central drivers of casualties and operational tempo. This dynamic underpinned grinding battles, most notably around Bakhmut, and framed Ukraine's 2023 counter-offensive, where progress was necessarily slower and more methodical against layered defensive belts. Russian attempts to regain momentum through meat grinder assaults and repeated armored attacks often produced high losses and limited gains in a trench and mines environment. Overall, the period highlighted Ukraine's growing demand for more artillery systems, ammunition, and ISR enablers, as the war moved from swift maneuver to sustained firepower, attrition, and endurance. Drone-centric warfare in Ukraine is best understood not merely as a technological shift but as an organizational and operational transformation aligned with Mosaic Warfare principles. Large numbers of low-cost UAVs have enabled a distributed sensing and strike architecture in which many attritable platforms operate simultaneously as sensors, relays, and shooters. Instead of concentrating capability in a small number of high-value platforms, Ukrainian forces generate effects through the flexible recombination of numerous small systems integrated into adaptive reconnaissance strike networks. This architecture enables rapid sensor-to-shooter integration, increases resilience through redundancy, and allows tactical units to dynamically assemble mission-specific tiles into operational kill webs. In this sense, the growing drone centricity of the battlefield reflects a broader shift toward distributed and modular force employment rather than simply the proliferation of uncrewed platforms. UGVs gained importance by 2025 for last-mile logistics and casualty evacuation, with the explicit aim of reducing human exposure to artillery and pervasive UAV threats near the line of contact. However, they are increasingly important for combat as weaponized platforms equipped with heavy machine guns. Concepts such as one operator supervising multiple UGVs, monitoring several camera feeds, and taking manual control only when a target appears, fit the broader trajectory: fewer people at the contact line, more sensors and expendable systems in the kill zone. Ukraine's deployment of low-cost, explosive-laden, maritime, uncrewed surface vehicles, USVs, has fundamentally neutralized the Russian Black Sea Fleet's regional dominance by forcing its major warships to retreat from Sevastopol to more distant ports, without a navy. In parallel with this maritime success, the rapid maturation of Ukrainian interceptor UAVs has added an increasingly decisive, low-cost layer to short-range air defense. By February 2026, systems such as Wild Hornet's high-speed Sting were credited with destroying more than 70% of incoming Shahd 136 Geran 2 type one-way attack drones over Kiev and its surrounding area, thereby reducing reliance on scarce Western surface-to-air missiles and preserving them for higher-end threats. The overall trend is unmistakable: the longer the war continues, the more clearly it resembles drone-centric warfare with small uncrewed systems, with an expanding contested surveillance and strike envelope that steadily raises the cost of movement, resupply, and concentration. Ukraine's rapid battlefield innovation in small, low-cost uncrewed systems has been driven by a decentralized ecosystem in which soldiers, volunteers, startups, and brigades adapt widely available civilian technologies into military capabilities at scale. Crucially, the decisive shift has depended less on technological breakthroughs than on the novel application and mass diffusion of existing technologies, with the report emphasizing that the real change lies not so much in technological innovation per se, but in the novel application of existing technologies. This ecosystem institutionalized a tight development combat testing modification combat testing cycle, with massive tactical experimentation, followed by widespread technological adoption by the armed forces, enabled by direct feedback loops between frontline users and developers that compress traditional R&D timelines from years to months. These patterns align closely with the Mosaic Warfare emphasis on distributed, disaggregated capability architectures and modularity, originally articulated by DARPA, which assembles many diverse tiles, with varying sensors and weapons, into mission-specific force packages to mass effects without massing forces. DARPA further highlights adaptability as a core driver, fielding large numbers of expendable platforms that can absorb losses while sustaining operational output. Emergence of adaptive kill webs. Ukraine's wartime trajectory points to the emergence of an adaptive kill web rather than a linear kill chain, because its combat software ecosystem, centered on Delta and linked with systems such as GIS-ARTA and Kropiva, operates as a federated integration layer that connects sensors, decision makers, and shooters across echelons instead of relying on a single fixed sensor-to-shooter sequence. Delta, a military situational awareness and battlefield integration platform, aggregates inputs from drones, satellites, stationary cameras, sensors, reconnaissance units, and other reporting streams into a shared operational picture, while Element supports secure coordination. Delta Tube distributes live video, and Mission Control assists flight planning, thereby sustaining rapid retasking under battlefield pressure. Within this wider architecture, GIS-ARTA, AC2, and Fire Mission Allocation System performs the function most closely associated with the often cited Uber for artillery analogy because it pools target data from drones, forward observers, radars, smartphones, GPS devices, and other sources, then matches the fire mission to the available artillery, mortar, missile, or UAV unit best placed to deliver the required effect with speed, accuracy, and economy. Kropiva, a frontline tactical fire control and navigation tool, complements this architecture by supporting mission planning, firing solutions, positional exchange, and offline operation under degraded connectivity, thereby preserving combat functionality when communications are contested or partially disrupted. Taken together, these systems allow Ukrainian forces to compress the targeting cycle, allocate fires dynamically, and reroute effects when particular nodes are jammed, degraded, or destroyed, which is why Ukraine's battlefield management increasingly resembles a kill web rather than a chain. Edge C2, and time compression through human-machine autonomy in Ukraine. Ukraine's human autonomy and initiative, delegated authority and decentralized tactical execution, is widely traced to post-2014 reforms and partner training that aim to decentralize command, professionalize the NCO Corps, and shift leadership culture toward mission command principles. A detailed academic account of Western training efforts reports that mission command was deliberately taught and modeled as an exportable expertise to enable faster subordinate action within the commander's intent, while also noting an implementation friction. Ukrainian counterparts lacked an equivalent term for mission command, and the concept clashed with Soviet legacy hierarchy and limited trust in operational practice. Early war evidence also indicates that Ukrainian units retained tactical initiative in rapidly unfolding engagements, acting effectively even when higher-level direction was incomplete or disrupted. This cultural permission to act effectively converts shortages in mass into tempo, allowing dispersed small units to compensate by making faster local decisions and exploiting fleeting opportunities, aligning closely with Mosaic Warfare principles of devolved execution and rapid recomposition. At the same time, multiple assessments caution that autonomy and decentralization have not been uniform. As the war scaled, some functions, notably the reconnaissance UAV screen, became more centralized at battalion and brigade level, and external observers describe the overall armed forces of Ukraine's command approach as a hybrid of NATO-style mission command aspirations and more centralized control tendencies. Style. However, practices vary across units and echelons, with some commanders embracing mission command principles while others maintain tighter control, reflecting both doctrinal uncertainty and individual leadership. Another defining feature of Ukrainian Mosaic Warfare has been the compression of sensor-to-shooter timelines through distributed ISR strike integration. Traditional targeting cycles, detect, identify, decide, engage, often required hours or days as information passed through command hierarchies and engagement authorities were obtained. Ukrainian forces compressed these cycles to minutes or even seconds by collocating sensors and shooters, delegating engagement authority to tactical echelons, and employing automated or semi-automated battle management systems. Furthermore, Ukraine has compressed the kill cycle by pushing sensing and strike decisions down to tactical UAV operators, while augmenting them with AI-enabled target recognition, tracking, autonomous navigation, and terminal phase target lock, thereby improving engagement of fleeting targets under contested electromagnetic conditions without eliminating human control over fire decisions. Technical and organizational adaptations. Platform heterogeneity and sensor integration. Ukraine's kill webs are built from a heterogeneous mix of commercial, improvised, and purpose-built military platforms. While such diversity would normally be seen as a liability in conventional force planning, because it complicates interoperability and increases the burden on training, maintenance, and logistics, Ukraine has turned it into an operational advantage. The use of multiple platform types and procurement channels has increased redundancy, enabled rapid substitution and iteration, and made it harder for Russian forces to suppress Ukrainian capabilities through platform-specific countermeasures. The platform mix includes small commercial quadcopters, DJI Mavic, Autel, and similar, for short-range ISR, improvised FPV racing drones adapted for kamikaze strikes, purpose-built loitering munitions, Switchblade, Phoenix Ghost, and Ukrainian-developed systems, medium-endurance tactical UAS, RQ-11 Raven, Puma, and equivalents, and larger operational-level systems for deep reconnaissance. Each platform class serves distinct roles, with significant overlap enabling substitution and redundancy. Sensor integration extended beyond tactical UAS to include national satellite reconnaissance, Western ISR assets, including space-based and airborne systems, ground-based sensors, and human intelligence networks. Ukrainian battle management systems fused these multi-source inputs, creating a layered ISR architecture with redundant coverage and multiple queuing paths. This integration, technically challenging given the diversity of data formats, security classifications, and organizational boundaries, was achieved through a combination of purpose-built software, commercial tools, and improvised interfaces developed by volunteer programmers and military technologists. Communications architecture and situation awareness. Ukraine's distributed kill webs required communications architectures capable of moving sensor data from dispersed platforms to shooters and battle management nodes under contested EMS conditions. Ukrainian forces employed a mix of line-of-sight radio links, commercial cellular networks, satellite communications, Starlink, and ad hoc relay techniques to maintain connectivity. This heterogeneous communications architecture provided resilience through diversity. When Russian EW disrupted one link type, alternatives could be employed, but the lack of standardized interfaces and data formats complicated automated fusion and cross-platform coordination. Ukrainian forces relied heavily on human operators to manually integrate data from disparate sources, increasing cognitive burden and limiting scalability. The vulnerability of communications links to Russian EW emerged as a critical friction point. Russian forces employed sophisticated jamming and spoofing against GPS, commercial cellular networks, and UAS control links, forcing Ukrainian operators to adopt countermeasures including frequency hopping, directional antennas, autonomous navigation, and reduced reliance on real-time links. The ongoing EW counter-EW cycle drove continuous adaptation in Ukrainian communications architecture, with both sides iterating tactics and technologies in a compressed timeframe. Within this heterogeneous communications architecture, Ukraine's Delta combat software has functioned as a cloud-based battle management and data fusion system, evolving from a situational awareness map, conceived by Aerorozvidka, into a platform that integrates radar, video, text, HUMINT, SIGINT, and partner intelligence into a single operational picture accessible from brigade to general staff level. Technically, Delta's Google Maps-like interface supports layered filtering, historical pattern-of-life analysis, and drone strike mission planning by highlighting electronic warfare-affected zones, helping translate dispersed sensor feeds into actionable tasking. Delta also sits within a broader combat software ecosystem, e.g., Kropova for most artillerymen, which the report credits with reducing targeting time from 20+ minutes to 1 minute, thereby shortening sensor-to-shooter workflows. Critical capability gaps and friction points. Technical gaps and challenges. Despite operational successes, analyses of Ukraine's wartime, kill web, Mosaic-style approach emphasize that technical and integration frictions can still constrain scalability and resilience under conditions of fragmented communications, heterogeneous equipment, and intense electronic warfare. A repeatedly identified gap is the difficulty of achieving standardized interoperability across a diverse ecosystem of sensors, communications links, and battle management tools that emerged and scaled under battlefield pressure rather than through a single, pre-planned enterprise architecture. In practice, interoperability has been uneven, with widespread reliance on manual workarounds, for example, transferring screenshots between applications when systems do not integrate smoothly. These workarounds keep humans in the loop for basic data transfer and correlation, increasing operator workload and limiting how far sensor-to-shooter orchestration can be automated at scale. The absence of plug-and-play standardization can be compared to the U.S. Modular Open Systems Approach, MOSA, which U.S. law defines as a modular design and interface strategy intended to support widely adopted standards and enable easier integration and replacement of components. By contrast, Ukraine's software and platform ecosystem has often had to grow together through pragmatic integration and workarounds, even as systems such as Delta are explicitly developed as integration platforms and tested against NATO interoperability standards to exchange operational pictures with allied systems. Accordingly, achieving stronger Mosaic warfare scalability is widely framed as an architectural challenge, moving toward open, modular data exchange approaches and common integration pathways that reduce the need for bespoke stitching between tools. A further technical gap concerns AI-enabled autonomy and C2, reducing susceptibility to jamming, limiting operator workload and human exposure, and enabling the synchronized employment of larger UXS groups increasingly requires onboard navigation, perception, and coordination functions that do not depend on continuous radio frequency links or the length of fiber optic cables. The next logical step is the development of networked, increasingly intelligent swarms, or, more broadly, coordinated groups of multiple low-cost platforms, supervised by a human operator who assigns objectives and constraints while the system autonomously distributes tasks across the group. Such swarms would contribute to a more seamless and sophisticated implementation of Mosaic warfare by enabling distributed assets to coordinate, reallocate functions, and generate effects with less human micromanagement. This promises better synchronization, deconfliction, and the generation of distributed massed effects across many platforms at once. At the same time, it increases the requirements for interoperable data exchange, secure mesh networking, and reliable edge fusion. As autonomy shifts from assistance functions toward target engagement and humans delegate increasingly complex tasks to AI-enabled systems, the degree of direct human control may erode. This, in turn, sharpens the legal and ethical concerns surrounding lethal autonomous weapon systems in the context of Mosaic warfare. Social and organizational gaps in implementing Mosaic warfare in the Ukrainian armed forces. Ukraine's ability to scale Mosaic warfare-like practices is limited by organizational friction, especially the difficulty of capturing, validating, and spreading rapidly changing lessons across a large wartime force. Although bottom-up innovation has produced effective local solutions, adoption remains uneven across brigades, and limits on integrating civilian technology hinder broader implementation. These gaps are reinforced by cultural differences within a multi-generational force that combines Soviet-style hierarchy with informal horizontal networks, making initiative and diffusion inconsistent beyond early adopters. Assessments note that Ukraine is moving away from centralized command, but lasting adaptation requires stronger training, learning, leadership, and doctrine to institutionalize new practices across the force. Distributed logistics, production capacity, and rapid obsolescence. Sustainment limits the scalability of Ukraine's attritable UXS model because large-scale use of low-cost, high-loss platforms creates heavy demand for replacements, batteries, spare parts, munitions, and repair capacity. Ukraine has sustained this model through commercial procurement, volunteer networks, and foreign support, but this largely ad hoc system faces clear limits as dispersed units also require local repair, forward stockpiles, and resilient distribution under contested conditions. These pressures make centralized logistics hubs increasingly vulnerable and push Ukraine toward more distributed, redundant sustainment networks with multiple supply paths. As UAV use expands from thousands to tens of thousands of systems, making institutionalized logistics, protected production capacity, and stronger maintenance infrastructure essential for sustaining combat power. At the same time, the fast measure-countermeasure cycle means many frontline adaptations become outdated before they can be fielded force-wide, complicating standardization, training, maintenance, and interoperability across mixed generations of equipment. Conclusion. The war in Ukraine shows that Mosaic warfare is not necessarily a far-future concept tied primarily to emerging and disruptive technologies such as quantum computing, hypersonic missiles, or other highly advanced breakthrough systems. Instead, the Ukrainian case demonstrates that many of its core principles can already be observed in contemporary warfare through the creative integration of existing technologies, distributed architectures, and adaptive operational practices. Although Ukraine does not explicitly use the terminology of Mosaic warfare itself, its battlefield adaptation nevertheless reflects many of the concept's central features. Most importantly, Ukraine has demonstrated the military value of distributed low-cost uncrewed systems, adaptive kill webs, decentralized decision-making, rapid sensor-to-shooter integration, and continuous battlefield-driven innovation. These practices have enabled Ukrainian forces to generate effects through a flexible combination of many smaller and often attritable elements rather than relying primarily on a limited number of highly integrated and expensive platforms. In this sense, the Ukrainian case suggests that the practical relevance of Mosaic warfare lies less in futuristic technology as such than in the ability to connect, recombine, and adapt heterogeneous capabilities more quickly than the adversary. At the same time, the war also underlines that Mosaic warfare is not simply a technical matter. Ukraine's success has depended not only on uncrewed systems and digital tools, but also on organizational and cultural factors, especially delegated initiative, rapid learning, close feedback loops between frontline users and developers, and a willingness to experiment under battlefield pressure. The effectiveness of such an approach, therefore, rests on the interaction between technology, command culture, and institutional adaptability. Mosaic warfare, in practice, is as much about organizational design and operational method as it is about hardware or software. However, the Ukrainian experience also exposes the limitations of the current maturity of implementing this concept. Heterogeneous platforms, fragmented communications, uneven interoperability, heavy electronic warfare pressure, manual workarounds, and persistent sustainment burdens all complicate the scaling and institutionalization of distributed combat systems. Ukraine, therefore, validates the operational relevance of Mosaic warfare while simultaneously showing how difficult it is to standardize, integrate, and sustain under conditions of attrition and constant adaptation. For Western militaries, the central implication is clear. Ukraine should not be treated as an isolated anomaly, but as a highly important indication that the logic of Mosaic warfare is already shaping successful contemporary warfare, even if it is not described in those terms. The key challenge is therefore not whether such a concept matters, but how doctrine, procurement, command and control, and sustainment must change to make armed forces more distributed, interoperable, attritable, and adaptable in future conflict. Author Bjorn Hoog is a researcher at Fraunhofer FKIE, where he works on technology and innovation management, with a particular focus on the synergies between civil security and defense. His research interests include defense innovation, emerging technologies, military adaptation, and the changing character of warfare. His earlier research addresses topics such as mosaic warfare, hybrid warfare, and the strategic implications of technological change. His academic fields include security and defense studies, innovation management, and international relations. The views contained in this article are the author's alone.
This was the Horizon Audiofiles, a podcast of the Defense Horizon Journal. For more information, go to www.tdhj.org. Thank you for listening.